chart now that we created as a class yesterday and plot these points. Okay, so what's convenient for you folks is that you have your T-chart, and then right below it you have this graph. So you're going to have to forgive me, especially if, hey, you're watching this at home. I'm going to have to toggle back and forth between the slides to get the points. The first function that we're going to spend a little bit of time graphing today is the function y equals the sine of x. And you'll see on this particular graph right now, there's some information on it that is not on yours. The information on my graph that's not on yours pertains to the scale. And do you see that I have the first tick mark on the x-axis as pi over 6 or 30 degrees? And then the second tick mark would have to be pi over 3. The first thing we have to do is scale the x and the y-axis so that we know where to plot these points. So I'm going to go ahead and take a second and get the scale for this particular graph. So I'm going to start at pi over 6. That tells me how to count off. So I'm going to count off 1 pi over 6, 2 pi over 6, but you can see that that already got taken over. 2 pi over 6 is the same as pi over 3. So that's 1 pi over 6, 2 pi over 6, 3 pi over 6 is just pi over 2. 4 pi over 6, that's 2 pi over 3. 5 pi over 6, 6 pi over 6 is pi. 7 pi over 6 doesn't reduce. 8 pi over 6 is 4 pi over 3. 9 pi over 6 is 3 pi over 2, or 270 degrees. 10 pi over 6. 11 pi over 6. And then lastly, we have 12 pi over 6, which our last tick mark is 2 pi. So you can see that the goal is to get one full period or one full cycle of y equals the sine of x to fit on your x-axis. To do that, you had to go from 0 to 2 pi. This is how long your poster was, if you'll think back to what you worked on in the library. It started at 0 and it stopped at 2 pi. Well, that's because that's one revolution on the unit circle. Questions about how I scaled the x-axis? Honestly, you could go by pi over 4s, you could go by pi over 3s, but to get a lot of detail on this first go around, I went by our smallest value on the unit circle. I went by 30 degrees or pi over 6. So that's why I did that. But honestly, the choice is oftentimes yours on how you want to scale the x-axis. After we scale the x-axis, you got to scale the y-axis. So here you'll see that I did my first tick mark. The first tick mark is a fourth, which is 0.25. So this next tick mark would be 2/4 or 0.5, then 3/4, which is 0.75, and then 4/4, which is 1. Ooh, what's that? 1/4 or 0.25. We turned these things into decimals, so we're going to graph the decimals. It's kind of up to you. Okay, can anybody tell me why I stopped at 1? Yeah, Michael? It's the biggest number on the unit circle. We go out no further than 1 radius on that unit circle, so that has to be our biggest number. Now, notice that I'm omitting, at this point in time anyway, the negative x-axis, but the negative y-axis we're going to need. So this will be negative 0.25, negative 0.5, negative 0.75, and negative 1. So I scale my x and my y-axis. After you have your scale, you're ready to plot your points. And this is where I have to toggle back and forth between slides. You have the points right in front of you. So to start off, we are graphing y equals the sine of x. So we're really going to pay attention to these first 2 rows. This is a T-chart. The x values, you'll notice, are all angle measures. And then I, for my y values, am going to plot the decimals that are listed in the row next to sine. So for instance, the first point on this particular graph that I'm trying to graph is going to be the point 0, 0. So I plot that point. 0, 0, you know it and love it as the origin. The next point that I'm going to go ahead and plot is the point pi over 6, comma a half, or pi over 6, comma 0.5. Pi over 6, comma 0.5. And then going back to my t-chart, the third point I have to plot is pi over 4, comma 0.7. Pi over 4, comma 0.7. But uh-oh, pi over 4 isn't on here. Does anybody know where it goes? Think about the circle and where pi over 4 is. What's it in between? Do you know, Richard? Which means it's between what two x values here? Yeah, very good. So pi over 4 is actually, it sneaks up on you, it's right in there. Because it's exactly halfway in between pi over 3 and pi over 6 on the unit circle. True story. Well thought of. I liked how you kind of made the connection in your response between degrees and radians. You're like, oh, well, pi over 6 is 30 and pi over 3 is 60. 45 is halfway in between those. So it has to be pi over 4, which is in between pi over 3 and pi over 6. So that's good. So I have to graph pi over 4 is 0.7. All right, go back. Then I have to graph pi over 3, comma 0.86. Yeah, that's all right there, I guess. And then, oops, wrong way. I have pi over 2, comma 1. So all the way up, we hit a max. And then we start to see, you know, some patterns. For instance, 3 pi over 4, comma 0.7. We start to see some values repeating themselves. So if you think about where 3 pi over 4 is, 3 pi over 4 is where? In between what two angles on here? Excuse me. You could look at your circle if you're desperate. Where's 3 pi over 4? Joey. It sure is. So 0.7. And what you see is this, you know, sort of like line of symmetry sort of coming out of this value right there. We're going to end up flipping the points to go down. So at 3 pi over 4, you're at 0.7. And then they do give us a couple more. For instance, pi, comma 0. And then I think it said 3 pi over 2, negative 1. And then 2 pi, comma 0. So you get this nice curve. That comes out of plotting y equals the sine of x. Questions about that? Comments, concerns? All right, good job. So what you just created was a little mini version of your spaghetti graph project. True story, you did. Okay, what I want you to do right now is take a minute and you're going to replicate this exact same process that I just went through. So I went ahead and I graphed y equals the sine of x, first by getting the scale, and then by stealing my points off of my t-chart that we made together as a class yesterday. I want you to go ahead and graph the sinusoid on the next coordinate plane in your notes. You're going to graph for me y equals the cosine of x. And I'm going to come around and check off your homework from last night real quick. So as I walk around, it looks pretty good. That is what the cosine graph actually looks like. Okay, now here's what I need you to do for yourself right now. It's almost like you need to develop a mental image for yourself, a permanent like tattoo on your brain of what cosine and sine look like. You just need to remember the general shapes. You already have this for some functions. True story. Like if I say y equals mx plus b, a shape does appear in your head. Hopefully it's a line. Or if I say y equals x squared, you know, you already have an image on your brain of what that equation looks like. It's a parabola. Y equals x squared is a parabola. Now what needs to happen to move forward in this class is for you to get a mental image. When I say y equals the sine of x, you know what that looks like. And then when I say y equals the cosine of x, you know what that looks like. So let's do that for a second. For instance, when I look at y equals the sine of x, I think it looks like a roller coaster. Like it starts, you know, maybe on like the racer, although the racer goes down first, huh? So does the jackrabbit. I don't really like roller coasters. The Phantom goes up first. The Phantom does go up first. You're right. So you want to think about a roller coaster that goes up first, and then and this does go like the Phantom does this too, right? Like you hit a peak first and then you head down. So it's a lot like, yeah, that. So it kind of reaches a peak, heads down into that valley where you think you're going to hit your head off the thunderbolt or whatever, and then you start to go back up again. So this to me looks like a roller coaster. I don't know what you think it looks like, but you need to like somehow retain the shape. So does anybody have another mental image of what this looks like? Like an S. I like it. Sort of on its side a little bit. Yeah, but for the most part, like some sort of snake or something. What do you think it is, Joey? Oh, half of like an infinity symbol. That's really good because that's math related, and we talked about infinity yesterday. Good. Okay, now the other image you need to tattoo on your brain is that. It's the graph of y equals the cosine of x. I often personally think this looks like a bowl or a fancy vase that has like a fluted edge to it, maybe like a piece of pottery. Like, here's like the little lip to the bowl, and then it comes down like that. I don't know what you see when you look at it. It's like one of those like weird psychiatry images. Like, what do you think this is? But this is not some sort of weird test. Jaden, like a U-shaped graph, kind of like a parabola, yeah. But it kind of does like branch out. A parabola just goes up and up and up forever and ever, but this one is going to be more periodic. We'll talk about that in a little bit. Like a C. Oh yeah, C for cosine. That's not bad. S for sine, C for cosine, C for cosentino. Who's on it? Good job. Questions about that? All right, well done. So now we need to, now that we have these like mental images of what these pictures look like, we need to pick out key traits, key points, if you will. We did do, correct me if I'm wrong, a vocabulary term yesterday. Lots of typos because I typed it really quickly. But we talked about the 5 key points, yes? Okay. The definition for 5 key points are the points that occur every quarter period. There are 3 types. The next couple of examples have you looking at the graphs that you just made, and you're picking out the key points. So these key points, again, are any maxes, mins, in other words, peaks or valleys in the graph, and then intercepts. So let's take a look at our key points now for sine and cosine. Example 1 has us picking out the key points for the graph of sine x. So y equals the sine of x, the one that looks like an S. Starts at the origin, increases to 1 at pi, at pi over 2, and then at pi it comes back down to 0. 3 pi over 2 it bottoms out at -1. 2 pi it reaches the axis again. So for example 1, we need to find the x intercepts. In other words, the places where y equals 0 for the sine of x. So we go back to the sine of x, and your x-intercepts are here, here, and here. So you got to write those down. What's up? You good? So the first one you would write is 0, 0. The second one you would write is pi, comma 0. And the third one you would write is 2 pi, comma 0. The next question they ask us in example 1 there. Whoops. I have a little smiley there. All right. So we had 0, 0, pi 0, and 2 pi, comma 0. And again, I don't know if you got to this point in your spaghetti project, but these questions are on like that last page there. So these come up again. Maximums are high points of the graph. Maximums are just points that are higher than all of the other points around them. So when I look at the sine of x, I see 1 peak. You see it? I see it. It's right there. Bam. Pi over 2, comma 1 is your maximum there. Does anybody see the minimum? Joey. Good job. Okay, quarter period. A full period for the sine and cosine curve. In other words, the time on the x-axis it takes for a graph to complete one full cycle went from 0 to 2 pi. The quarter periods occur every fourth of 2 pi. In other words, they occur when you cross through your quadrants. So really your quarter periods are the same as your quadrantal angles. So when we talk about the first quarter period, and we're going to go back and label these now on our graphs. When we talk about quarter periods, we talk about ways of chunking this graph into 4 equal pieces. If I take this sine curve and I cut it into 4 equal pieces, 1/4 of the graph is at pi, from 0 to pi over 2. The second part of the graph, or the second quarter period, or the halfway point of the curve, is at pi. We get through 3/4 of the rotation, or 3/4 of the graph. So there's my 3/4 period mark at 3 pi over 2. And then we finish the cycle for this curve at 2 pi. So this is our full period mark. The next questions ask you, what points do you see at these quarter period marks? So when you look at these questions here, what they're asking you is, what point do you see at the first quarter period? In other words, at pi over 2, what point was there? Well, at pi over 2, we said it before, we saw a maximum. That was the point pi over 2, comma 1. At the halfway mark, we saw an intercept. At pi there, we saw pi comma 0. At the 3/4 mark, in other words, at 3 pi over 2, we saw a minimum. Oops, comma -1. And then at the full period, we saw an intercept. And that was the point 2 pi comma 0. The domain, again, we talked about that yesterday for a good bit of time, is the space that the graph took up on the x-axis. So one period of this curve went from 0 to 2 pi. If you're using the interval notation that we used yesterday, you would put 0, 2 pi, and it stops. But honestly, these graphs can go on and on and on forever and ever and ever. But one full period goes from 0 to 2 pi. The range, which is what we talked about yesterday, is the space the graph takes up on the y-axis. Does anybody know what the range of this function is? The range. Not 0 to 1, -1 to 1, yeah. So the space this graph took up on the y-axis went from -1 to 1. That's it. Can't go any higher or any lower. We usually go smallest to largest. So the range, you could say it goes from -1 to 1, or you could say -1, 1, inclusive. Those are actual points on the curve. Now you get to do this. Answer these same questions now for cosine. You're going to go ahead and do that. So you want to take a second, review your answers to example 2 there. Does anybody have any questions about this as they look at their graph? Please remember, these points are designed to help you out with your project. So refer back to them as you're doing that yellow packet over the weekend. Okay, as promised, I did